Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Kean Fallon, who is a graduate student at Iowa State University. We're happy to have him here today to tell us that the Symplectic Zauner's conjecture is the Skew Hadamard conjecture. Take it away, Kean.
Thanks, John, for the introduction. Thanks to all the organizers for having me. I'd also like to shout out how awesome it is that you do this summer series to give the opportunity for people like me, a graduate student, to talk. And John, I'd also like to shout you out in particular for all the guidance that you gave throughout the course of creating this talk. So the title of the talk, as John said, is the Symplectic Zauner's conjecture is the Skew Hadamard conjecture. So this is really sort of the summary of the main result that we're going to see. Some of you might know what the second thing is. Most of you probably don't know what the first thing is. And throughout the course of this talk, I'll tell you what both are and why they are the same thing. So if you can remember this title, that'll be like a good bullet point. You'll be in good shape. Before we go much further, all of this research was advised by Joey Iverson. That's my PhD advisor. He's a cool guy. If you know him, you know he's a pretty smart guy too. Here's a photo of him. If he's got his camera still on, you might be able to catch a live version of this photo. So for today, I want to go through an outline quick. We're going to go through some background. I'm going to tell you about some basics about what ETFs are in Zauner's conjecture. And then I'll talk about defining ETFs in real symplectic space, whatever that means. And then I'll detail the main results a little bit more thoroughly, and we'll start to prove it. And part of this proof is kind of tricky. And so we're going to need to identify some combinatorial structure behind ETFs in real symplectic space. And by doing this and leveraging it, we can finish this proof. And at the end, I have something called an epilogue. And this is just a couple slides that will tie up some of the discussion that we have along the way. So first, I want to start with some background. I want to tell you what an ETF is, and I want to talk about sort of the space that we're going to be working in. So here's the setup. I have a sphere, maybe a unit sphere in R3, and I'm going to put some points on it. And these points, they naturally want to be away from each other. They repel each other. So when 2 points are close, there's sort of a high potential energy in between them. And their natural position here is to sort of be equally spread out. Now, I'm interested in when they're at their natural position or when they're the most spread out they can be. So I want to study sort of like the energy of this system. Now, what I'm going to do is I'm going to assign unit vectors to these points and put those vectors in as columns of a matrix phi, because I like to do linear algebra. And then I need sort of a measure of like an energy-like kind of function. And for that, I'm going to use something called coherence. This measures the maximum of the modulus of the pairwise inner products of these vectors. And because they're unit vectors, this is the modulus of the cosine of the angle between them. So when 2 points are close, the angle between these two things is going to be small, and the cosine will be large. And then as that angle gets larger, that cosine will get smaller. So with this modulus here, what I really need to do is include the negatives of these vectors. And the picture that I actually have sort of looks like this. It looks like 6 lines intersecting a ball. And then remember, I'm interested in when these things are equally spread out. So the goal here is going to be to minimize this coherence. So coherence is a lower bound. It's called the Welch bound. It's just in terms of the number of vectors I have in the ambient dimension. And I have conditions for equality on this bound. Equality holds if and only if the phi that I have is an equiangular tight frame. And by this, I mean for this first word, equiangular, I want the off-diagonal entries of the gram matrix to all be uniform modulus. And then tight frame, this is like a spectral condition here. It tells me what the minimal polynomial of the gram matrix divides. And then it tells me that the rank of the gram matrix has to be equal to the ambient dimension. Okay, so all these three things combined, those are the conditions necessary for a ETF. And this, as you can see in this top left picture, these ETFs have like a really nice structure. And a natural question to ask is, how many of these equiangular things can I fit in a given vector space? We don't always know the answer, but to help us, we have something called Gerzon's bound. And it says that for an equiangular set of n vectors in FD, n is at most d times d plus 1 over 2, if f is the reals, and at most d squared if f is the complex numbers. And equality, if I get equality in this bound, if I saturate it, then the thing I started with was an ETF. So just a little proof in quotes or a proof outline for you. What I'm going to do is I'm going to make these outer products of these vectors are necessarily Hermitian. And then the key part is that equiangularity here is actually going to imply that these outer products are linearly independent. And really, at this point, these outer products live in the space of D by D Hermitian matrices. So because they're linearly independent, I can have at most a dimension's worth of them. And that dimension changes based on whether you are over a real field or a complex field. So closely tied together with Gerzon's bound is this big open problem, famous conjecture called Zauner's conjecture. And it states that Gerzon's bound is saturated for every dimension over C. So this has applications in like compressed sensing and notably quantum information theory. But the big takeaway that I want you to know here is that, again, this is a big open problem. A lot of people really care about it, and it's very hard. So only finitely many dimensions are known for which Gerzon's bound is saturated over C. In particular, like this is like on the order of 200 or so. There's numerical evidence for more dimensions than that, but we actually really only know for not very many dimensions. So because I care about this problem, and because this problem is so hard, one of the pathways open for us to try to hope to make some progress is to vary the problem a little bit. So if we vary the problem, maybe we can make some headway there and then try to apply this lesson back to the space that we care about. And the spirit of this talk is in such a variation. So what we do here is we're going to change the setting to a symplectic one. And the first question that you might ask is, why even bother with this? Is this meaningful? I'm going to try to answer this by starting off with the motivation here. So a couple of years ago, a few authors, some of whom are in this virtual room right now, published a couple of papers studying ETFs over finite fields with geometries that are analogous to real and complex inner product spaces. One door they did leave open is a symplectic geometry. But in order to know what to do with ETFs over a symplectic geometry in finite fields, one would likely need to know what symplectic ETFs look like over a real symplectic space. So that was like kind of the motivation, but ultimately we want a connection back to the space that we care about. And in this symplectic setting, it turns out that ETFs in real symplectic space do have a connection to complex ETFs. And in fact, we can be inspired by this connection. We are inspired by this connection, and we actually end up we utilize this sort of connection to find complex ETFs of sizes that were previously not known to exist. And I'll talk about this a little bit in the epilogue. This isn't related exactly to the main result, so this is sort of one of those side things, but you'll see it at the end. And then lastly, I think the problem is interesting in its own right. So if you recall what the title was, basically as we switch to a symplectic setting, looking for the things that we care about is finding those things is like finding things that people have been trying to find for a very long time, for over 100 years, and that Hadamard matrices. So ultimately, we're tying symplectic Zauner's, a symplectic version of Zauner's conjecture, to a much older problem that is open and very difficult in its own right. So now that I've sort of given you some motivation as to why this is a meaningful move, I want to talk about what exactly I mean by real symplectic space. What is the space we're going to be operating in? So I want to let D be even. Symplectic space is an even dimensional space. And I'm going to define this block matrix omega. It's just got these blocks down the diagonal. And you're going to see this matrix in a few slides. I'm going to ask you to identify it. So just try to keep your brain on that for a second. With this matrix, I'm going to define this map. It takes two vectors x and y to x transpose omega y. And a notable property of this map is that it is alternating. So any vector against itself is 0. Down here, I've given an example in R2. This is just a simple example that hopefully you can verify, and then extrapolate that example to a higher dimension and see that it always holds true. Okay, so this map is called a symplectic form. And the space that I'll be working in is a real vector space equipped with this symplectic form. And throughout, I'm thinking about a symplectic form is not an inner product, but I want to think about it as playing the role of an inner product. So that's sort of what I'm going to be using throughout all of this. So this is it for the background. Now that we know kind of what space we're going to be in, it's time for us to define ETFs over this space. So in this section, I want to talk about ETFs in real symplectic space, what they look like, and I'll give you some examples. So we're going to do this definition via an example, essentially. So if you recall at the beginning when I defined an ETF in the sort of the standard setting, it was all about the Graham matrix. The Graham matrix is calling all the shots. So I'm going to do something similar here. I have this phi dagger phi, and I want you to think this dagger is playing the role of the adjoint, and that it's built in such a way that when I do phi dagger phi, it is truly the matrix whose ijth entry is phi I against phi j in this symplectic form. So this is something that I'm going to call like a symplectic Graham matrix. Okay, so because of this, remember this is alternating. The symplectic form is alternating, so I'm going to have zeros down the diagonal. And then if I want to be equiangular, I need to have uniform modulus entries off the diagonal. So let's throw that in there. I just have this alpha here as a placeholder. But when the characteristic of my field is not 2, which is the case when I'm the characteristics obviously not 2 over the reals, then alternating implies skew symmetry. So wherever I have an alpha, I'll have a negative alpha on the other side of the matrix. So the Graham matrix that I'm looking at here is skew symmetric. Now, this symplectic space, the symplectic form doesn't give rise to a norm here. So what I can do is universally scale this phi so that my alphas are a number that I want. And I'm going to do that so that all my alphas are 1 or negative 1 here. And this is just for the sake of this talk, this is going to be nice for me. And this is what I'm going to take as the definition of equiangularity in symplectic space. So that is all the off diagonal entries are plus or minus 1. I still need to handle the T and the F. First, we'll handle the T, so it's tightness. Here, this looks a little different. It is still a spectral condition on the Graham matrix. Now, my Graham matrix here is real and skew symmetric. So its non-zero eigenvalues have to be purely imaginary, and they come in conjugate pairs. So that's why you sort of have this extra power on the left side, and you have a negative number on the right side. So really what it comes down to is that tightness is the Graham matrix cubed is a negative multiple of itself. It satisfies this cubic. Okay, so in general, we'll say that tightness is just the Graham matrix is a negative. The Graham matrix cubed is a negative multiple of itself. And then lastly, this frame business. Well, this is still a rank condition. It's actually going to be the same thing as the normal setting. So the rank of the Graham matrix here will be equal to the ambient dimension. So here, the rank of this Graham matrix is 2, and in general, it will be D. So for those of you who do stuff with frames, you might be curious about the frame operator. For those of you who don't know what that is, it's just sort of changing the order of phi and phi dagger here. In general, the frame operator in this space is not always nice. For example, the frame operator here is this thing. This is not even unitarily diagonalizable. It's not normal. For that reason, we really only talk about the Graham matrix in this space, and that's what we're going to talk about moving forward. So because everything that I've given you so far has been all about the Graham matrix, right? It's Graham matrix this, Graham matrix that. One would hope, I haven't talked really about phi itself, one would hope that I can recover phi from its Graham matrix. I really sort of need that to talk about ETFs strictly by their Graham matrices. And I can do that. And I'm going to show you how that works right now. So the idea is that if I have a skew symmetric matrix that, I'm going to put this in quotes, looks like a Graham matrix of an ETF in real symplectic space, it is one. And what I mean by that is if I have a skew symmetric matrix G that satisfies the necessary properties, then in fact I can pull a symplectic ETF out of it. So here I have such an example. G is a skew symmetric matrix. It satisfies the cubic that I need for tightness. And I've actually given you the spectrum of G here because you'll be able to get the rank from that too. And here's how it's all going to work. I'm going to use the spectral theorem for real skew symmetric matrices. So this is just a version of the spectral theorem. And what it says is that I can decompose G like this. Here, the U is a real orthogonal matrix. And the thing in the middle is a block matrix, and those root 3s there, they correspond to the eigenvalues of G. So what I'll do now is this thing in the middle is a block matrix. So let's write U in blocks too that correspond to those sizes, because I want to be able to do some block matrix multiplication here in a minute. Now I'll factor out that root 3, and this is what I have. Now, does anybody recognize that top left block? You'll have to say it, or I don't know. I can't. So I don't think I can see the chat window.
Used for the symplectic form.
Yeah, that's right. It's the omega. So that's omega in this case. It's only the 2x2 version. But now that I have this, I'm just going to do block matrix multiplication here, and this is what I have. So I can write G as alpha times U1 transpose omega U1. And this right equality I haven't really told you about, but in fact, this U1 dagger is equal to U1 transpose omega. And I won't tell you exactly why, but this is the case. And what that allows me to say is that if I set phi equal to the square root of alpha times U1, then G is in fact the Gram matrix of phi, the symplectic Gram matrix of phi. Okay, so now that I have this in my back pocket, what I want to do is only talk about Gram matrices from here on out. And then the next slide, I'm going to talk about examples. It's going to be a whole family of examples of these ETFs in real symplectic space. And really, it's going to be examples that are they're going to be the Gram matrices of these symplectic ETFs. Okay, so this family of examples, they all come from Skew Hadamard matrices. Maybe that's not a surprise given the title. But an n by n Skew Hadamard matrix is a square matrix whose entries are plus and minus 1. It's scaled orthogonal. And in particular, when I subtract the identity, I get something that's skew symmetric. So this implies necessarily that the Skew Hadamard matrix has all positive ones down the diagonal. Now, I want to say that from each of these Skew Hadamard matrices, I get two different examples of ETFs of two different sizes in the real symplectic space. And I'm going to show you both of those right now. And at the bottom here, I have boxed sort of the conditions that I need to check. So I want to say that the things that I have here on the left and the right side, those are going to be Gram matrices of ETFs in real symplectic space. So first, let's handle the left side. Let me direct your attention over there. So I'm going to subtract the identity. And what I have left is something that is known. It's called a skew conference matrix. It's skew symmetric. It also happens to be a scaled orthogonal matrix. In particular, it satisfies SS transpose equals n minus 1 times the identity. Now from this, we can see immediately two of the conditions are satisfied. So we know that the off-diagonal entries are all plus or minus 1. That's pretty immediate. And this is a scaled orthogonal matrix. So necessarily, if this is going to be the Gram matrix of an ETF, its rank is n. So this ETF would be an n by n ETF. The last thing I have to check is this middle condition here, that's the cubic, right? Well, I know that S is skew symmetric, so I just want to apply the fact that S transpose is equal to negative S, and then I'll move that negative over to the other side, and I see that I have S squared as a negative multiple of the identity. Well, then all I have to do is multiply by S again to see that S satisfies this cubic that I want. So what this tells me is that S is, in fact, the Gram matrix of an n by n ETF. Now, for the right side, what I want to do is I want to subtract the identity again, and now I want to look at the bottom right corner, in particular the n minus 1 by n minus 1 bottom right corner. So there's like a padding of a vector on the left and the top. And this I'm going to call the core, and it immediately, you can see it has off-diagonal entries plus or minus 1. It's skew symmetric. And because HH transpose is equal to n times the identity, you can figure out that CC transpose has to be this n minus 1 times the identity minus the all ones matrix. Okay, and that will also tell you that the kernel of C is spanned by the all ones vector. So what this tells me is that C is rank efficient and has a one-dimensional kernel. So the rank of C will be n minus 2. So if I get an ETF out of this, it will be n minus 2 by n minus 1. Now, all I have to do is check this middle condition again, this cubic. So I'm going to apply the same thing that I did in the previous example. C transpose is negative C. I'll move that negative to the other side. You can see that change there. And then I'll multiply through again by C. Now, I have that c cubed as a negative multiple of c, but I have this cj on the other side there. But remember that the kernel of c is spanned by the all ones vector. So when I multiply c times the all ones matrix, I just get 0. So in fact, c does satisfy this cubic, and I have the Gram matrix of an n-2 by n-1 ETF on my hands. Now, as you probably just saw, I mashed that button a little too fast and gave you a little preview. But the idea, the main result of this talk is that the arrows go in the other direction. Okay, so when I have an n by n ETF, I can get an n by n Skew Hadamard matrix. And actually, that's not too bad. That's why it's sort of this pale red arrow. We can see this pretty quickly. Now, on the other side, when I have an n-2 by n-1 ETF, I can also get an n by n Skew Hadamard matrix, but this is more difficult, and it's going to make up sort of the meat of the rest of the talk. All right.
Kean, can I ask you a question real quick?
Yes, sure.
This is dishonest to me because I know the answer, but I want to clarify for everyone else. Can you go back a little bit? I just want to show when you define the core there, you normalized that Hadamard matrix, right? Like
yeah, and that's right. In this case, the Skew Hadamard matrix that I gave you was already normalized. So what I mean by that is it's got all +1s along the top and then -1s along the left side. So actually, I guess a better idea would be to look at the Skew conference matrix here. Yeah, so I slid that under the rug. But yeah, okay. That's right. This is the core of a normalized Skew Hadamard matrix.
Yeah. And that's how you end up with that Jn-1 when you do transpose.
Yes.
That's where that comes. Okay, yep. Cool. Thanks. I just want to clarify.
Okay, so I want to talk about the main result in a little bit more detail. So I need to give you what symplectic Zauner's conjecture is. Now, symplectic Zauner's conjecture was closely related to Gerzon's bound, so it's natural for us to have a symplectic version of Gerzon's bound, and that's where we'll start. So the symplectic version of Gerzon's bound says that for a set of equiangular vectors in d-dimensional symplectic space, and is at most d+1. So this is very restrictive, much more than the regular case. And it really just gives us a window of two possibilities, that n is either d or n is d+1. And I'll give you a proof hint. The general idea is that when n is even, you can find that the Gram matrix is invertible. The symplectic Gram matrix is invertible. And that tells you that the vectors that you started off with were actually linearly independent. And when n is odd, you can remove one of these vectors and apply the even case. And that's sort of how you get this difference of 1. Okay, now one might expect that symplectic Zauner's conjecture is just symplectic Gerzon's bound is saturated for all d. That's not the case, actually. So I'll state it for you right here. Symplectic Zauner's conjecture actually sort of removes one of these two possibilities, depending on if you're a multiple of 4 or not. So if you're a multiple of 4, you're equal to 2, you can only have a d by n or a d by d ETF. And when you're not a multiple of 4, that is, you're 2 mod 4, you can only have a d by d+1 ETF. So but really, symplectic space is a very different space. And therefore, I mean, it's going to look a lot different. One other thing I want to point out here is that symplectic Zauner's conjecture is actually just saying something about the existence of ETFs in real symplectic space in general. So this is a statement about the existence of all ETFs in symplectic space. But I really want you to think that, in some sense, this is the natural statement of Zauner's conjecture in the symplectic space. Okay, so at this point in my talk, maybe some of you that have seen a couple of my talks are surprised that you haven't seen a meme yet. I had a hard time figuring out where to put them. So with that in mind, I'll show you the next slide. This slide serves two purposes. It fills my necessary minimum meme quota for a talk, and it also reminds everybody of where we're going. So this only thing that I haven't talked about really explicitly yet is on the left. So I'm going to do that now, and then we can talk about the main result. So the Skew Hadamard conjecture states that if n equals 2 or n is a multiple of 4, then there exists an n by n Skew Hadamard matrix. So this is sort of similar in spirit to Zauner's conjecture. It's talking about the existence of these things that people like to find. And then the main result looks like this. So this is really just that diagram that we had from a few slides ago, but I've attached these two conjectures on the top and bottom. So really the statement of this main result lies in the arrows here. That is, if I have an n by n Skew Hadamard matrix, I get these symplectic ETFs of different sizes. And if I have those symplectic ETFs of different sizes, then I get an n by n Skew Hadamard matrix. So that's really the main result I really like to think of as being this diagram. And now that we have it, I'd like to start walking through a proof. One thing that's sort of immediately apparent, based on the fact that this is just the diagram from a few slides ago, is that these down arrows we've already talked about. I've showed you how to get an n by n ETF in symplectic space and an n minus 2 by n minus 1 ETF in symplectic space from one of these Skew Hadamard matrices. So we're good there. We've already done that. Now, if you recall, also in those slides, I told you that the arrow on the left side, that was easier than the arrow on the right side. So let's do the easy arrow first. I'm going to let G be a gram matrix of an n by n ETF here. Now, G necessarily satisfies this cubic that I need it to satisfy. G is also invertible and skew symmetric. Invertible because it's the gram matrix of an n by n ETF. And it has plus and minus 1 off the diagonal. Now I'm going to apply this invertibility and skew symmetry. I'm going to multiply by an inverse, and I'm going to change one of the G's to a negative G transpose. And what do I get but this? So here I have GG transpose as a positive multiple of the identity. But I sort of know what G looks like. In fact, any row of G is just going to be a bunch of plus and minus 1s and a single 0. Okay, so when I do GG transpose, that's like the Euclidean gram matrix of the rows of G. And that tells me that all of these diagonal entries have to be n minus 1. That's the norm squared of every row. So I know exactly that GG transpose is, in fact, n minus 1 times the identity. So therefore, G is a skew conference matrix. All I have to do is add the identity, and I get back to a Skew Hadamard. All right, well, this arrow on the right is all that's left. It's a little bit more tricky. The goal is kind of the same, or the procedure is kind of the same. What I want to do is I'm going to make this, if you remember on the right side of that diagram from earlier, we were talking about the core. And what I want to do is make this gram matrix and insist that it's like the core of a Skew Hadamard or a skew conference matrix. So this is the idea. I'll let phi be a d by d plus 1 ETF in real symplectic space. Now, a little aside, just so people don't get confused, I will see that this D will end up being congruent to 2 mod 4. So I really want to think that this D is in playing the role of n minus 2 here, and d plus 1 playing the role of n minus 1. But I don't want to talk too specifically about that. I'm going to let G be the gram matrix, the symplectic gram matrix of this phi. And then I want to build this matrix over here on the right. And this S is what I hope is a skew conference matrix. So I'm going to insist that SS transpose is a positive multiple of the identity. And what turns out what needs to happen is this X that's around this G, it has to be in the kernel of G. This is fine because G has a non-trivial kernel. And I want to scale this X to have norm squared d plus 1. By norm squared, I mean like X transpose X. Remember, I am in a symplectic space, so maybe that's a little confusing. So X transpose X is equal to d plus 1. Now, what I need here, it turns out that if I do this, all this sort of algebra works out. But what I need to have happen is I need that X has to be flat. That is, that X has uniform modulus through all of its entries. And because of the way that I've sort of scaled it, what that'll say is that the entries of X are plus or minus 1. That's actually all I need to finish up this proof. Now, this is not immediately obvious. And how I need to show you that this is true is by identifying this underlying combinatorial structure. So in this section, I'm going to talk about that combinatorial structure, and we'll use it to finish off the proof of this result. So here's a map of exactly what we're going to do. I'm going to start with a d by d plus 1 ETF in symplectic space. I'm going to look at its gram matrix, and then I'm going to show you a graph that it corresponds to. And that graph will be actually a type of tournament. Now, within this graph, I can count a certain subgraph, and this subgraph is called a diamond. And if I have the right number of them, then I will have up to some notion of equivalence, I'll actually be a doubly regular tournament. This is a really nice kind of tournament, okay? And then from this information, I can gather that the kernel of this matrix was flat. Okay, so we have to talk about the first arrow first. This is going in chronological order here. This is the map. So let's do that now. On the top left here, I have the gram matrix of a 6x7 ETF in real symplectic space. And on the right, I have the tournament which it corresponds to. And what I mean by that is that I want you to think of the matrix on the top left that's rows and columns as being indexed by a vertex set. And when I have a plus in the ijth entry, that means I have an arrow from I to j. And if I have a minus, it goes the other direction. Now, if you notice, I won't say much about it, but this gram matrix is a very particularly nice example of a gram matrix. So let's talk about properties of this graph. It's directed, it's complete. So because all of my off-diagonal entries are plus or minus 1, I have an entry in each one of them. So there's an edge going between any pair of vertices. But I have more than that. So I also have that all of my vertices have equal in and out degree. And what I mean by that is that every vertex has the same number of edges coming in as it does coming out. And that number is the same amongst all vertices. So I'm going to pick on vertex 1 here. If you notice, it has 3 edges coming in and 3 edges coming out. And this is encoded in the matrix on the left. I can just check a row and count its minuses and its pluses. But more than that, it also has something, it also has this equal in and out codegree. And what that means is that if I pick a pair of vertices, they have the same number of shared in neighbors as shared out neighbors. So here I'm going to pick on 1 again, and then I'll pick on 2 as well. So that'll be my pair. And if you notice, 2 and 1 have 1 shared in neighbor and 1 shared out neighbor. And how I can identify this in the matrix on the left is that I just pick the 2 rows that correspond to my vertices, and then I find those shared minus or plus signs that line up in a column. Okay, well, the thing that I actually care about, there's a key property that this thing has. This thing is called a doubly regular tournament, and that is the kernel of its matrix is spanned by the all ones vector. Well, this seems almost a little bit too nice to be true, because remember I said this was the gram matrix of a symplectic ETF. And in general, it is. So in general, when I have the gram matrix of a symplectic ETF, a d by d plus 1, it does not correspond directly to a doubly regular tournament. And so there's a way of sort of getting around this, and I'm going to talk about that here in the next slide. So first I need to talk about something called switching. Switching is like picking a vertex or several vertices in this graph, and then just taking all of the edges that come in and all the edges that come out and changing their direction. So here, let's look at vertex 2 because it's the topmost. And I'm going to switch on vertex 2. So just look at this, look at vertex 2, and then when I switch slides, you'll notice that all of the arrows have switched direction. So what this looks like on the left is when I have my original matrix in the middle, I'm multiplying on the left and right by this diagonal matrix D, and it has 1s in every diagonal entry except the second entry, which is a -1. And what this has the effect of doing is multiplying on the left by this D, it flips all the signs in the second row, while multiplying on the right flips all the signs in the second column. So the thing I get at the end looks like this. And one noticeable thing is that the original matrix I started with, that was the matrix that corresponded to a doubly regular tournament, its kernel was spanned by the all ones vector, whereas this new thing, its kernel is spanned by a flat vector. So in general, the gram matrix that you're given, if I have a d by d plus 1 symplectic ETF, it's not going to be the gram matrix of a doubly regular tournament. What I need to show is that I can do some sort of switching to it and get to a doubly regular tournament. And if I can do that, then I know that the kernel will be spanned by a flat vector. But if I'm given the arbitrary, like an arbitrary grand matrix of a symplectic ETF, this is impossible to do. I don't know where all the signs are, right? So luckily, there's a different approach that avoids like having to try to determine what the right switching is. And this is due to a theorem, due to Belkouche, Boussoudi, Lakhlifi, and Zaidi, just a few years ago. It says if the number of vertices I have is 3 mod 4, and I have something like, it's called these diamonds, if I have a maximal number of them, whatever that means, then I'm switching equivalent to a doubly regular tournament, which is good enough for me. Now, this maximal number of diamonds, this is actually a number. So when the number of vertices is 3 mod 4, this is a function of the number of vertices. So I can check against it. I can check to see that I have this many. And this is like an invariant under switching. Okay, so I want to think about this with like an analogy. And so bear with me on this analogy. The goal here, I want to think about these tournaments as like Rubik's Cubes or things that look like Rubik's Cubes, okay? So a doubly regular tournament is like a fully solved Rubik's Cube. It's got all the colors, you know, all of its faces are one color. It's nice and neat. And then switching is like moving those things around, essentially, right? Making it messy. Now, there's a game that we're going to play where I'm the judge, and you're going to try to tell me, I'm going to hand you something that looks like a Rubik's Cube, and it might not be. It might not even be solvable. But your goal is to tell me, is this thing solvable? Now, you're going to get handed this thing blindfolded. And trying to find the right switching here is like trying to tell me that this thing that I've handed you is a solvable Rubik's Cube by just trying to solve it with your hands. But you're blindfolded. That's impossible, right? But you're clever, so you realize that all you have to do is ask me a few questions. In fact, you say, well, I can't see this Rubik's Cube, but does it have exactly 6 distinct colors? And I'll say, yeah. And then you say, well, do each of those 6 colors show up exactly 9 times? And I'll say, yes. And then all you have to ask me is, do each of the centers of the faces, do they see a different color? Are each of them a distinct color? And if I answer yes, if I'm nice and I answer all your questions, then you know this is in fact a genuine Rubik's Cube and it can be solved because it can see all those permutations. You have enough information. So really this move that we're doing where we're counting the maximal number of diamonds here, it's like, it's impossible for me to try to prove to you that something is solvable here by solving it blindfolded or trying to solve it blindfolded. But I can ask you the right questions and count some things, and I can tell you that this is solvable or not. So because this whole thing is crucial to this proof, I better tell you how to count these diamonds. And that's what I'll do on this next slide. So the key here is going to be that the characteristic polynomial of my grand matrix will count these diamonds. And first I want to tell you what a diamond is. So here are the four tournaments up to isomorphism. That is the tournaments on 4 vertices. Now these first 2 on the left, these are diamonds. So they are comprised of a 3 cycle and then a single vertex where every edge either comes into or out of that vertex. Now these other 2 are not diamonds. So the diamonds are just described as they are on the left. Now what's useful for me, and that's somebody who likes linear algebra, is that I can completely separate these 2 classes by their determinant of the matrix that corresponds to them. So diamonds have determinant 9 of that matrix, and the other ones have determinant 1. So what that means for me is that I can look at my original matrix G, this grand matrix that I had, and I can look at just a 4x4 principal submatrix. Now this will correspond to a 4 tournament. That's a subgraph of the graph that this whole thing corresponds to. And all I have to do is check its determinant to figure out if it's a diamond or not. In this case, the determinant is 1, so I know that this is not a diamond. Now I can check another principal submatrix and check its determinant. In this case, it's 9. So this is a diamond. So the idea here is that I can look at the principal minors of this matrix to figure out how many diamonds I have. So in general, this gives me the following, that the sum of 4x4 principal minors of this matrix G, it's going to be 9 times the number of diamonds in its corresponding graph, plus 1 times the number of things that aren't diamonds. Now, because there's only 2 classes here, I can write the number of not diamonds in terms of the number of diamonds. and then just get a nice tidy equation. So at this point, remember I talked about the characteristic polynomial, so where does that come in? Well, if you recall, I can write the characteristic polynomial, it's not that I can write, it's just that the characteristic polynomial of any matrix, the coefficients of that thing are related to the principal minors of that matrix. So here, all I have to do is go find the right coefficient. So if I find the right coefficient, now I know that this is related to the 4x4 principal minors, and I have these two equations, one on top and one on bottom, and I just stick them together, and I can figure out that the number of diamonds I can write in terms of this one coefficient and n, the number of vertices. So at this point, this is actually enough for me to finish the proof, and I'm going to walk you through that right now. So here, we're going to start off with this d by d plus 1 ETF in real symplectic space. I'll make it symplectic gram matrix. And then this is the key step here. Tightness allows us to count the diamonds. Why is this true? Well, tightness, remember, was a condition on the spectrum. It tells me what the minimal polynomial divides. I also know what the rank of G is, and I know that G is skew symmetric, so in particular, it's diagonalizable. So all this information together is going to tell me exactly what the characteristic polynomial of G is. So I can just compute it. And then I go find that coefficient. And once I find that coefficient, I can find the number of diamonds that I have. So here, the number of vertices in particular will be d plus 1, because that's coming from my gram matrix. Now, there's a short little aside that I'm not going to talk about. But remember, in order to use this result of having the maximal number of diamonds, I needed that d plus 1, or the number of vertices, had to be 3 mod 4. And so there's a little lemma that I use here that ensures this is the case. So once I have this, then I know that the matrix, my gram matrix, corresponds to a graph that's switching equivalent to a doubly regular tournament. And because this is true, I know that its kernel is spanned by a flat vector, hence x is flat. Okay, so in this last section, which I'm calling the epilogue, what I want to do first is I want to sort of expand upon what we just talked about, this combinatorial structure. That'll be this first slide. And then in the last slide, I'm going to give what I promised you to give at the beginning, which is this connection to complex ETFs. So first, let's talk about this maximal diamond business. So from this last section, I said that if I had a d by d plus 1 symplectic ETF, that d was 2 mod 4, and I was like switching equivalent to a doubly regular tournament, right? My underlying graph was. But in this setting, in this case, for d congruent to 2 mod 4, this is the same as a tournament with the maximal number of diamonds. Okay, and what I'm trying to get at here is this isn't just true for d by d plus 1 ETFs. It's true for d by d ETFs too. So if I have a d by d ETF, then d is 0 mod 4. Actually, it can also be equal to 2. But either way, I have a tournament with the maximum number of diamonds. So how does this work? Why is this the case? Well, here's why. So I'm going to let S be the matrix of an n tournament. So its off-diagonal entries are all plus or minus 1. And I know a row of S looks just like ones and negative ones and a single 0. So when I do this SS transpose, I'll have n minus 1 down the diagonal, and I'm not sure what's off the diagonal. Okay. Well, it turns out there's another way to count diamonds. And it's following this formula here. I'm not going to get into it. But what it is it's some function of n that's the number of vertices. It's just a complicated function of n. It's not important. You shouldn't think about it. But then I have this sum. I'm subtracting off this sum of the off-diagonal entries squared. So when I fix the number of vertices, when I fix an n, this f of n is fixed, and then I'm trying to like maximize the number of diamonds there. This is like minimizing the sum of the off-diagonal entries squared. And because it's a sum of squares, the best I can hope for is that these off-diagonal entries are all 0. Well, when this is the case, that means S is actually a skew conference matrix. Remember, that was a scaled orthogonal matrix that satisfied S transpose equals n minus 1 times the identity. But I know I showed you earlier that if I have a d by d ETF, that its gram matrix is a skew conference matrix. So the whole the whole point of this slide is that behind every symplectic ETF is a tournament with this maximal number of diamonds. Okay, last slide. It's all about finding complex ETFs. So this is the connection. Now this is a kind of a broad strokes thing here. So essentially this connection that I'm talking about is I have this complex D by N matrix, and I can get a real 2D by N matrix by taking the rows of that thing and splitting them into real and imaginary parts. And when I do that, if I look at the complex gram matrix of the thing on the left and take its imaginary part, then I'm going to get like the symplectic gram matrix of the thing on the right. So this is sort of the connection. Maybe morally, you could think of it as the complex inner product is a sum of a symmetric bilinear form and a symplectic bilinear form, which are the real and imaginary parts, respectively. So how am I going to use this? Well, I know I have this connection between symplectic ETFs and Skew Hadamard matrices, right? Hand in hand. So one would think that in the land of Skew Hadamard matrices, if I have some constructions over there, I should be able to do something similar in the land of symplectic ETFs. So here I have a non-trivial construction of Skew Hadamard matrices that is pretty straightforward. What I do is I take a skew conference matrix, and then I make this 2x2 block thing. Now, when I add an identity to this, I'll have a Skew Hadamard matrix. So this is called doubling because it's doubling the size. And what actually happens is there's an analogous thing that exists in the land of symplectic ETFs. So here, phi is a D by D symplectic ETF. But the thing that I want to point out that's the difference here is that, remember, a skew conference matrix was the gram matrix of a symplectic ETF. So the Skew Hadamard doubling is sort of like doubling a gram matrix. But in this proposition here, what I'm really doing is doubling the ETF, not the gram matrix. Okay. So now remember, I have this connection that I sort of vaguely talked about up here at the top. In this connection, what it allowed us to do is inspire this theorem about complex ETFs, and that is the following. This is called ETF doubling. It's from a different paper. It says that if I have a D by almost 2D real or complex ETF, then I can double that ETF in the following manner. Here, F is the ETF, and this G at the bottom, that's the Neimark complement. So through this theorem, we were actually able to prove the existence of D by 2D complex ETFs that were not previously known to, in sizes that were previously not known to exist before, including as small as an 11 by 22. And then we found that numerically some of these things existed, and we found all these examples. We actually conjectured that these D by 2D complex ETFs exist for all D. And then after this, there's a sequel to this paper that explores this topic further. It has lots of cool results and strengthens that conjecture. So the upshot of this whole slide, and the whole point of this thing, is that we sort of check the box in saying, is there a lesson to be learned by studying the symplectic ETFs? Is there something that we can apply back to the setting that we care about? We answer that yes. And it's not just non-trivial stuff. It's actually good information. Okay, that's all I have for you. I'd like to thank you all. Open the floor for any questions. I have the two papers, the D by 2D papers I just talked about. I'm referencing them here at the bottom. The contents of the stuff in the slides is currently being written, and I hope to have it posted on archive soon.
All right. Thank you, Kean. I'm going to react to this talk by clicking buttons.